The other thing we need to consider about different sources of radiation, or the different types of radiation I should say, are their properties. So not all the different types of radiation are equal. They have different properties that we need to consider. So in order to consider those, we'll sort of tabulate this a little bit. I'm not going to bother drawing table lines in because my straight line drawing on a tablet isn't so great. But we'll look at these categories. So the type of radiation, the composition, so what it's made of, the range, and the ionizing ability. Now when we talk ionizing ability, if you are to ionize, or if an atom becomes ionized, it means it's lost electrons. The reason why that's important in terms of biological systems is that if you've got atoms in cells, if some of those atoms lose their electrons, it means they're going to behave differently in a chemical sense. So if ionizing ability can have an impact on biological cells, which can then cause things like cancer. So we need to know how ionizing these different types of radiation are. So we'll go in order as we've looked at them already. So for an alpha particle, we know that that's a helium nucleus, so 42He, which is basically 2 protons and 2 neutrons. The range here is largely determined by the size of the particle itself. So because the large size comparative to other types, so the large size and mass means that it's not particularly penetrating. So it's low penetrating ability. And what we mean by low penetrating ability is that it can be absorbed by fairly straightforward sort of substances, really. So alpha radiation will be absorbed by your skin, so it won't pass any further into you than your skin. It can be absorbed by paper. So if you've got an alpha source near you, just hold up a piece of paper and you'll be right. Or even a few centimeters of air. So if it's if the source is a few meters away from you, then you don't really have to worry about the alpha radiation, because air will actually stop the alpha particles from traveling too far. Now on the flip side to that, alpha particles have very high ionizing ability. And that's basically for the same reason why it has a low penetrating ability. Large size, large mass, it causes those alpha particles to frequently collide with target atoms. So because it's a larger particle, it's going to collide more frequently with target atoms in whatever by target atoms we just mean anything that the alpha particles are traveling towards. So that's alpha. If we look at beta, we're just going to group beta plus and beta minus together because they're largely the same, just the only thing that's different is the charge. So we've already seen for beta plus that it's a positron, and for beta minus it's an electron. And in both cases they're emitted from the nucleus. And if you compare the size there, a positron or an electron significantly smaller both in size and mass when compared to an alpha particle. So as a result it has a fairly moderate penetrating ability. Whereas the alpha particle was very low, we've now got a fairly moderate penetrating ability. And that's due to the smaller size. And when we say moderate, similarly to above, we can identify a few things that would absorb beta radiation. So it's absorbed by a few millimeters of aluminium. So you just say, I don't know, a couple of Coke cans kind of thing would absorb beta radiation. Also absorbed by a few centimeters of body tissue. So it can pass a little bit further into the body compared to alpha. So it can pose a little bit more of an issue for some of the cells that might lie closer to the surface of the skin. So it's certainly getting in a little bit further than the skin. And the last thing that it can penetrate is about 25 centimeters of air. So again, beta source, if it's far enough away from you, then it's not really problematic at all in terms of the direct effect that it would have on you. When it comes to ionizing ability, it's now got a moderately high ionizing ability. So it's not as high as alpha. And again, that's because we're still going to have the ability to ionize, but because the particle itself is so much smaller, its ionizing ability is going to be much lower. So it's going to be much less than alpha due to less frequent collisions with target atoms compared to alpha. So when we're talking about these terms of moderately high and very high, it's very much just sort of ranking them. It's not necessarily a specific measurement. We're not going to go into the detail of the measurements that would be involved in this sense. We're just looking at the comparisons between them. The last one then is gamma, and gamma is a high frequency electromagnetic wave or high frequency electromagnetic radiation. So note that term here, magnetic radiation. It doesn't necessarily mean that it's so the term radiation can be used somewhat interchangeably, whether it's nuclear radiation or if it's just electromagnetic radiation. So light, infrared, ultraviolet, they're all forms of electromagnetic radiation. Another way to think of it too is that it's a photon of energy, so a particle of energy that's released during radioactive decay. Now, gamma has high penetrating ability, and the reason for that is that it's basically a massless particle. So because it has no mass, it doesn't interact the same way that alpha and beta do, and can therefore pass much further through matter. So some examples again. So it would be absorbed by a few centimeters of lead, and lead's a very dense metal. So it still takes quite a lot of the lead to absorb the gamma, whereas beta would be easily absorbed by a few centimeters of lead. It can also be absorbed by a few meters of concrete. So that's why power plants generally have fairly thick, nuclear power plants generally have fairly thick concrete walls to absorb any radiation that might sort of stray away from a nuclear reactor. Now, in terms of the radiation that would be passing through human bodies, very little of it would actually be absorbed, considering how far gamma can penetrate. Because the human body it doesn't contain very dense atoms, like lead, for example, means that a lot of the gamma radiation that you might be exposed to would actually pass through you quite easily, and so not much of the cells in the human body would absorb gamma radiation. On top of that, gamma has fairly poor ionizing ability. So whereas alpha and beta were relatively high, gamma is fairly low, as it doesn't readily interact with matter because it's a photon of energy. So the fact that it's a photon of energy and not a particle with mass, it means then that it's going to be much less ionizing than what alpha and beta are. So there's a summary of the properties of alpha, beta and gamma radiation. Now, to try and define which one is the most dangerous, it's pretty difficult. ionizing ability is the one that you'd probably most look towards for looking at how dangerous it is. But if you then consider the range at which it can penetrate, then you can see that while alpha might be the most ionizing, it's also the least penetrating. So it's not an easy discussion to have as to which one's the most dangerous. In the end, if you've got any of them in extremely high amounts, then it's going to be problematic. When it's much lower amounts, then it's a little bit more of an issue of how to shield it, so that you, whether it's say beta and you need a little bit more shielding, so more aluminium for example, or if it's alpha where you need to make sure you're just further away from it, or make sure you've got something that can absorb it, such as paper. So it's a few different aspects that you'd need to consider in terms of trying to define which one's the most dangerous, or given that you know that one of those is going to be prevalent, what are the safety aspects that you need to consider.